Okay, welcome back. So if you recall, we are discussing LED. In the last class, we had introduced what LEDs are, how they work, the basic operational principle and so on. So today we shall continue the discussion. So LED is the reverse of photodetectors and solar cells. You convert electrons and holes or electrical energy into light energy. We have to make a distinction between visible LEDs that our eyes can perceive and IR or UV LEDs that our eyes cannot perceive, but those are useful for other application. When we talk about things like brightness, color rendering and other things, we talk about only the visible LEDs which human eyes can sense, right. In general, many of the electrical and optical properties of LEDs will remain same whether human eye can sense or not, but only the things like brightness, colors, chromaticity, all these things are related to the white LEDs or the colored LEDs which human eyes can perceive. Okay, please remember that. So in the last class I told you that, in the ending of the last class I told you that LEDs are not monochromatic, which means LEDs do not emit only a single wavelength. There is a range, it's a distribution of wavelengths, and that spread of that wavelength will depend on lambda. Shorter wavelength LEDs like blue or UV will have a shorter spread, and higher wavelengths will have a higher spread, if you recall that, right. So LED is not strictly a monochromatic light, although I perceives it to be like a monochromatic light, and this spread in its wavelength comes from the Fermi distribution and the density of states. If you recall, I had introduced joint density of states that takes into account both electron and hole effective masses together as a harmonic mean, that's called reduced effective mass, and from there we derive this expression for the intensity versus the wavelength, and we saw that there is a spread in that, right. So let's come to whiteboard now, and we'll continue with where we had left yesterday. So I told you that LED, the process is called electroluminescence. I hope you remember that. Electroluminescence is the process of emission of light from LED. What happens is that if you have a PN junction, and then you are injecting electrons and you are injecting holes, then they recombine, and that energy that is lost is given out as photons. If the energy is these electrons and holes are recombining radiatively from band to band. Okay, these photons will come out at an energy corresponding to the band gap. Ideally it should come out at a wavelength of lambda equal to hc by Eg, but I told you it comes out slightly more than that because there is a distribution. In the EK diagram, the electrons will be like that, holes will be like that. So there will be a small distribution here. Because of that, the peak will be slightly shifted. Now it is not necessary that it's always a PN junction, although PN junction will give you efficient LEDs, but somehow if you can basically make electrons and holes recombine, the emission of light, that process is called electroluminescence or EL. Okay, please keep that in mind, electroluminescence or EL. I told you the first electroluminescence was observed in 1907, which is more than 110 years back, and it was actually observed in a material that you even cannot expect it to exhibit EL. It was in silicon carbide, which is an indirect bandgap material. So of course it was very inefficient, very poor. Nevertheless, first PN junction LEDs based on gallium arsenide and other things, they came out in the range of 1949 to 1962. In this range, gallium arsenide, although gallium arsenide wavelength is not exactly in the visible spectra, towards the tail of the red, near IR, but PN junction and LED on gallium arsenide was invented by this person called Nick Holoniak, right, who also wanted the Nobel Prize, but he didn't get it, of course. So anyways, and then the work on LEDs has started a lot in 1970s, 80s and all. Many companies in Japan and US were very much into big time R&D development of LEDs of different materials. People realized that this gallium arsenide phosphide, indium gallium arsenide phosphide, InGas, all these LEDs were they were taking place. I mean, the research was going on not only for visible but also other applications. But gallium arsenide phosphide LEDs were pretty dominant in a way, because they were able to get all this red, yellow and other emissions. But green was a problem, blue was a problem. So only in 1990s, this Japanese team of Nakamura and Nakamura and these three gentlemen, Amano, right, Akasaki, these guys got the Nobel Prize in 1990. In 2014 they got the Nobel Prize for a work that they did in 1990s. They essentially enabled the InGaN LED, InGaN blue LED they enabled. Okay, it's a PN junction essentially. So they got the InGaN blue LED, which you can convert to white by using a phosphor coating, and that's why that makes possible our white LEDs that are used in our homes and garages and streets and all. Okay, so that LEDs are eventually done, but there's a lot of history, lot of historical accounts are there as to how this research was going on, how many setbacks were there, how people had fired them from companies, and all these things are there. You can read up in the internet. Okay, that's an important thing, but we should be aware that this was the track of development of LEDs. And even today there's a lot of research going on, especially in green LED, because green is not very easy to emit. Even for gallium nitride technology, green emission efficiencies and are actually not as close to blue emission efficiencies, because for green you need a higher indium composition in InGaN, and a higher indium composition in InGaN is difficult to grow material wise. Okay, please remember that all these materials are not silicon, these are compound semiconductor, gallium arsenide phosphide, indium gallium nitride, InGaAs and so on. And whenever I say compound semiconductor, there's a lot of material science that has to go into it, in terms of the lattice mismatch, in terms of the structural quality, in terms of the strain. It's a humongous amount of material science research that goes into enabling these layers, because whatever layer you grow, InGaAs, InGaP, whatever, these have to be grown crystalline, very high quality crystalline solid. If they are not, then non-radiative recombination center will be large. That means if there are defects, and other kind of material imperfections, you will get non-radiative recombination that will kill your efficiency. Okay, that will reduce your efficiency and even make your device not emit any light. So your material has to be of superior quality, of superior material structural quality. And so there's a lot of material science that makes sure that these layers that you're growing are of very high quality. Okay, you should remember that making something emit light is more difficult than making something absorb light and give photoconductivity. So it's easier to do research on photoconductivity than to do on LED, because light emission is a very complicated process and very difficult. Okay, so you need to wear the best quality of material there. Okay, anyways, so apart from white light LED giving us all these lightings and all, there are many applications of LEDs. Applications of LEDs, of course lighting is the most important application now, because everywhere you see white light LEDs. You also have a lot of applications in displays, these billboards, computers, games, automobiles, clocks, and everywhere, the backlit, the back panel, mobile phone, all these displays depend heavily on LEDs. Okay, also you have to remember that things like fiber optic communication, they use LEDs that are not visible to human eye. InGaAs LEDs they use for near IR 1550 nanometer communication, optical fiber communication. You also can use deep UV LED, which emits at around 260 270 nanometer. That is also the emission of mercury lamp, by the way, to kill bacteria and sterilize water. So there are many applications that way. Okay, many applications of LEDs. So it's a very vast and growing field, but you should know what is the hot area now if you want to do any research and all. And in all cases, the LED is basically, I keep telling you, it's basically a PN junction. But the problem with a simple PN junction is that when electrons and holes are injected by a forward bias, the electrons and holes are expected to combine here and emit light, but they might move very fast and they might not get time to recombine. Then you will not get a very bright LED. And secondly, the diffusion of holes and electrons might be very long. If this depletion width is, for example, 1 micron, suppose I am telling you, okay, and the whole diffusion length LP and LN, the diffusion lengths are say 5 micron, suppose, then in 5 micron 1 electron and 1 hole will recombine to give 1 photon. But your depletion is so narrow, 1 micron, that you have very less chance that electrons and holes will recombine. So the emission will not be there. So you want to confine the electrons and holes, you want to confine the carriers, so that they get to spend more time in times of recombining. Okay, so that they can spend more time and they have a more probability of recombining with each other to emit light, and that's why you confine them. And the confinement is enabled by a quantum well. I keep telling you this. So it's your right, this is your N type, this is your P type. So when you inject holes from here, when you inject electrons from here, if electrons falls down here, holes falls down here, then the electrons and holes will not be able to come out because there is a barrier. It's a quantum well. See, it's called a quantum well. Okay, in case you have forgotten, this is called a quantum well. Carriers are confined here, and because they are confined, the carriers are confined here, and because they are confined, they are not able to move out. No, so they will get a better probability of recombining now. Better probability of recombining, and of course the material has to be direct band gap material in all this, so that when they recombine, they will recombine radiatively and band to band, and it will emit a wavelength corresponding to this. But in reality there will be like a subband level here. So it will recombine from the first subband E1 to first subband E1 here. So it will be slightly more than the band gap of InGaAs or whatever you are using here. You see my point, right? If the band gap of this quantum well is suppose 2 eV, the emission of the light will be slightly more, maybe 2.2 eV or 2.3 eV, because it is a quantum well. In a quantum well you have subband levels, if you remember high school physics. So that subband of the electron quantum well, subband of the whole quantum well, it will recombine from subband to subband. Okay, and so it will be slightly more, like you have this and you have the whole here. So it will basically recombine from this to this. from this to this. So that energy is slightly more than this. That's why you will get a peak at a slightly lower wavelength or higher energy. This is the reason why you have quantum well LEDs, so that you confine them, you increase the probability of them recombining well. Okay. In reality, of course, people what they do is that, suppose you have one quantum well like that, this is your whatever. So you have one quantum well, then when you are injecting electron, some electron might fall here, but some might go actually. Some electron might fall here, some holes might go, some might go, because they also are, you are injecting at high energy. So what many people do is that they have multiple quantum wells. So what I mean by doing that is that you will have one quantum well, then you have a barrier, again another quantum well, another barrier, again another quantum well, another barrier, and go like that, right? Or maybe it will go like that. Okay. So then you will have like that, you will have a quantum well, you will have a barrier, you will have a quantum well, barrier, like that. You see. So this is one quantum well, this is one quantum well, this is one quantum well for electron. Similarly, quantum well for hole, quantum well for hole, quantum well for hole. These are barriers. The barrier can be a little wider bandgap material, of course. These are barriers. These are barriers. Okay. So what you do is that by increasing the number of quantum well, when you are injecting electron, you make sure that they fall. Okay. You make sure that they fall, and you have a better chance of making them recombine. This is called a multiple quantum well MQW structure. Okay. Most of the LEDs are like that, multiple quantum well structure. So you cannot give 3 quantum well or 5 quantum wells are more than enough. It's no need to grow like 10 quantum well or 100 quantum well, because there is no improvement eventually. I mean, only in 3-5 quantum well you will get some improvement. Also material wise, growth wise, there are some challenges, but this is what people do. Okay. And in some case, these are all the interesting things that you should be generally aware of in terms of designing. So for example, if you are using a gallium nitride, blue LED, InGaN blue LED, you are using an N-type gallium nitride, a P-type gallium nitride. So these quantum wells could be InGaN 10%, which is a lower bandgap material to emit blue, right? And the light that comes out, the photon that comes out, will correspond to the bandgap of InGaN, the quantum well, slightly more because of the subband level, but still substantially lower than the bandgap of GaN. So the photons that come out will not be absorbed in this P-type or N-type GaN, because the P-type or N-type GaN is a wider bandgap material compared to the photon energy of InGaN, which is a smaller bandgap material. So the photons can come out without getting absorbed, which is a beautiful thing of quantum well. If you do not use a quantum well, just a p-n junction, then the photon that comes out has the same energy as the P-type and N-type layer. So they get absorbed in the P-type and N-type layer. They do not come out. So that is not good. So quantum well offers two advantages. One is that it confines, hence increases the chance of recombination and increases the brightness of LED or efficiency. Secondly, the light that comes out will not be absorbed, so you can extract the light as in a more efficient way. Okay. So these are the two main advantages of using quantum well. People use a multiple quantum well structure, typically 3 to 5 quantum wells, and each of the quantum well layer could be, the range could differ. It could be between 3 to 6 nanometer, could be even slightly more, slightly less, depends. And the barrier could be also, in the same range, maybe 4 to 10 nanometer, depends. Okay. So in the typically in few nanometers. So this kind of precision will need you MOCVD or MBE to grow. MOCVD or MBE systems, these are epitaxial tools, very sophisticated epitaxial tools to grow these materials one layer by one layer, while maintaining a super high crystalline quality of the layers, so that the non-radiative recombination doesn't take place. So these are very lot of things that are going behind LED production and LED research. Okay. So that I told you about the quantum well LED, multiple quantum LED to get high radiative efficiency, right? So now that I was talking about efficiency, I'll talk that there are two kinds of live recombination. Even if I take a quantum well or a non-quantum well LED, I'm just drawing one quantum well, that is also fine. Sometimes what happens is that this quantum well can be little, typically it's around say 3 to 6 nanometer or so, but some people do, they only have one sort of structure like this, where they don't have a very thin layer, they will have a slightly thicker layer maybe. It's not exactly a quantum well, and this thickness could be maybe, it depends, it could be maybe 10 nanometer or maybe even 20 nanometer, and only one of these will be there, not multiple. This is not exactly a quantum well, this is called a double heterostructure LED. Okay, one of the first blue LEDs was made on this kind of structure only. It is little wider, it is not too thin to be quantum well. A quantum well is such that your electrons or holes can move only in XY direction, not in the Z direction. This is the Z direction of growth. So your carriers that are confined cannot move in the Z direction. What I mean is that actually when you grow the layers, you will grow like this, you will grow like this, right? So this is your layer stacks that you are growing. Maybe in between you have an InGaN layer or whatever, then the confinement, if it happens here, this is your z direction, carriers cannot move in this direction, they can only move in x and y direction. That is why it is called quantum well. You are confining it to 2 dimension. In the third dimension it cannot move because of the barrier. Okay, but in double heterostructure LED it is not exactly a quantum well because you gave it wider. Typically the thickness of the quantum well T should be in the order of de Broglie wavelength of the electron. In that case you call it a quantum well. Okay. Anyways, so this is also called double heterostructure LED, but in general whether you talk about a multiple quantum LED or a PN junction without any quantum well, we are talking about the double hetero junction, anything you can talk about, but eventually there are 2 types of recombinations that carriers will take place. The electrons and holes need to recombine, right? There are 2 types I told you. Of course, one is called radiative recombination, which is the band to band radiative recombination, and one is called the non-radiative recombination that does not contribute to light, that kills your efficiency. This non-radiative recombination could be Shockley-Hall-Reed recombination, that is the trap assisted, or at high injection density it can be Auger recombination that I had discussed, and the radiative recombination is typically band to band recombination. Okay. Now each of these categories of recombination has its own lifetime. So radiative recombination has a lifetime of tau rad, okay, and non-radiative recombination will have a lifetime of tau non-rad. Okay, these are lifetimes. Okay, these are lifetimes. Now the question, the interesting thing is that the rate of recombination, the rate of recombination is actually inversely proportional to the lifetime. So the rate of radiative recombination is inversely proportional to the radiative lifetime. Similarly, the rate of non-radiative recombination is proportional to 1 by the non-radiative lifetime. So what does it mean? Okay. It means that if you have a shorter lifetime, you recombine more. Now there is a radiative recombination, there is a non-radiative recombination, both will take place in a material. You want that most of the recombination should be radiative, very few or almost nothing should be non-radiative, which means you want the radiative recombination rate to be higher, right, and you want the non-radiative recombination rate to be lower, which means you want the radiative recombination lifetime to be as short as small as possible, okay, because it is inversely proportional now, and you want the non-radiative lifetime, you want them to be as long as possible or as large as possible. So when I say if you have a radiative lifetime, suppose your radiative lifetime is 1 nanosecond, that means after every 1 nanosecond carriers, electrons and holes, this is your Fermi level, whatever, I am not drawing very well, okay, your electrons and holes are coming, electrons and holes are recombining here to emit photon, that is radiative recombination. So at every 1 nanosecond your electrons and holes are recombining radiatively to emit light, that is a good thing. And suppose your non-radiative recombination is 1 microsecond, that means after every 1000 nanosecond or 1 microsecond you have 1 electron recombine with some defect or holes non-radiatively or whatever, that is good. If on the other hand the reverse happens, which means every 1 nanosecond your carriers are recombining non-radiatively to defects, and in 1 microsecond, every 1 microsecond your carriers will recombine radiatively to emit light, then practically you will get no light, because in the time duration delta t that you recombine 1 electron and 1 hole to give you 1 photon, in that already 1000 electrons and 1000 holes will recombine not to give light. So if you have a fixed number of electrons and holes that you are injecting by applying a voltage, then you see in every delta t time you will have 1 electron and 1 photon emit light and 1000 electrons 1000 holes not emit light. That means your efficiency of LED emission has gone to the dogs, there is no emission there. Okay. So internal quantum efficiency or NI, this IQE is defined in a way as the non-radiative lifetime divided by non-radiative lifetime plus radiative lifetime. You want the radiative lifetime to be as small as possible, so that electrons and holes recombine very fast radiatively, so that you get most of the emission as acceptable light. Okay. So if your radiative recombination rate the lifetime, sorry, if the radiative recombination lifetime is as small as possible, then this quantity will approach 1, because it is like x by x plus y, where y is very very small, then it will become 1, no, that is the same thing. Then your internal quantum efficiency will become 100%. So, you want the radiative recombination lifetime to be as small as possible compared to non-radiative lifetime. Okay? Please keep that in mind. When I say non-radiative lifetime, it includes Shockley-Hall-Reed and Auger recombination both. Okay. The total recombination rate, okay, is proportional to the entire number of free electrons and number of free holes, and it is the proportionality constant is given B into n into p. This B is actually a constant. It is called the bimolecular, because there are two molecular species, bimolecular rate constant, Okay. So, the radiative recombination rate, okay, is actually the total recombination rate minus the thermal generation. Now, the thermal generation is nothing but this bimolecular rate constant into equilibrium electron into equilibrium hole, okay, equilibrium before you are injecting anything. So, and you know that delta and the excess electron is nothing but total electron minus equilibrium electron, excess hole is nothing but total holes minus the equilibrium holes, right. So, essentially your radiative lifetime is given by the total, I mean these quantities are same, by the way, excess electrons that you are injecting divided by the radiative lifetime, that is your radiation lifetime, okay, and it comes out to be 1 by bimolecular rate constant delta n, that is the excess electrons you have or holes, whatever, it is the same quantity, plus equilibrium electron plus equilibrium hole. This gives you the radiative lifetime. So, higher radiative recombination rate will give you shorter radiative lifetime, and that is better, okay. And it depends, if you have higher equilibrium concentration also you will get lower radiative lifetime. You have to also inject excess carriers, by the way, okay. This is just, you should keep that in mind. For low level injection matlab you are biasing the LED at a lower voltage so that your current is little low. So, at lower level injection your delta and the excess carrier is much lower than your equilibrium carrier concentration, in which case your radiative recombination lifetime, this quantity will be proportional to 1 by B into N naught plus P naught, because this delta N will be much smaller, okay. Please remember that. And of course, if you are talking about high level injection, which means you are biasing the LED at very high voltage, you are getting a lot of injection, then your excess carrier concentration is much larger than your equilibrium concentration, and then your radiative lifetime is almost proportional to 1 by B times delta N, okay. Just to keep in mind, just in case, okay. Anyways, so that is good about it. So, I talked about IQE, and then there is of course EQE. I will just quickly finish the efficiency part. EQE is essentially given by the external quantum efficiency, similar to photodetectors, is the inverse. In photodetector, it was the number of electron hole pairs coming out of the device divided by the number of photons falling on the device. Here it will be number of photons coming out of the device which is emitted, that is coming out of the device. You do not care how many photons are generated in the quantum well or in the active layer, because many of the photons may not come out, they might get absorbed or lost or whatever. You are concerned with how many number of photons are emitted and what is the number of carriers you are injecting to the device. You do not care how many of these carriers actually reach the active region, the quantum well. Many of the carriers you are injecting by applying the voltage may not even reach the quantum well, they might get lost in metal contact and so on, other things. But your external quantum efficiency is how many photons you are emitting from the device divided by how many carriers you are injecting, okay. So, of course, the number of photons that is emitted here, this number of photons that is emitted here per unit time, if you are emitting at a particular wavelength lambda, is P out, that is the output optical power you are getting. Remember, output optical power divided by Hc by lambda, and the number of carriers that you are injecting is nothing but the current that you are supplying, that you actually, the current voltage. LED is a forward bias junction, by the way. So, you will look like this, right, it is looking like this. So, you will bias at some forward voltage, no. So, what is the current here, maybe 20 milliamp or whatever, that 20 milliamp or whatever current you are pushing is the I, and I by Q is actually the number of carriers per unit time, okay, is the unit time. But now of course, please remember that your LED is not emitting at a single wavelength, it is a range of wavelength. I am talking about the peak wavelength here, okay. Most of the power will be near the peak wavelength only. Now, because you are applying some voltage here V, you are getting some current here I, maybe 10 milliamp, 20 milliamp, the input electrical power you are giving is V times I. You agree? V, that is the voltage you are applying, maybe 5 volt, 3 volt, who knows, and the current you are getting maybe 10 amp, milliamp, 20 milliamp, whatever. The product is the electrical power you are getting. This is different from the optical power output you are getting. Remember that, okay. So, if this is the case, then you know this number of carriers injected is the total current coming out of the device divided by Q, which I can write as, from here I can write I equal to P in by V, right. P in by V, that is current, right, by Q. So, this is your P in by V by Q is your. So, what I can do is that external quantum efficiency is number of photons emitted, P output by Hc by lambda divided by I by Q. So, I can write that as P out by into lambda by Hc into 1 by Q by I is nothing but P in by V. So, V can go up, right. So, essentially your external quantum efficiency is P out, which is the optical output power, by input electrical power times Q lambda by Hc into V. Okay. Okay. Now, this quantity, the output optical power, this is quantity, this is external quantum efficiency by the way, EQE. This quantity is output optical power, divided by input electrical power is called, this quantity is called wall plug efficiency. Okay. It is a very important quantity in LED literature. Wall plug efficiency is defined as the output optical power you are getting by the input optical power you are supplying. Suppose you have this IV, no, you have this IV. Suppose you are applying a voltage of say 4 volt, and you are getting a current of say 20 milliamp, and the LED is emitting bright blue light, suppose. Then the input power you are giving is 4 volt into 20 milliamp, which is nothing but 80 milliwatt of power you are giving input. Now, what is the brightness of the LED? You can measure it in an integrating sphere. There is a tool to measure how much power is coming out in terms of optical power. If the power that is coming out is 10 milliwatt of optical power, then your wall plug efficiency will be 10 by 80, which will be how much? Very low, no? It will be like 12% or 12.5%. Okay. So, like that, okay. So, that is wall plug efficiency, and now from this you can say that this is equal to wall plug efficiency times Q lambda by Hc into V. In other words, I can say that external quantum efficiency by wall plug efficiency, okay, is equal to Q lambda by Hc into V. Okay, Q lambda by Hc into V. Okay, wall plug efficiency. Now, the problem is that your the statement is that your external quantum efficiency divided by wall plug efficiency, this ratio will always be greater than equal to 1, which means external efficiency will be always slightly higher than wall plug efficiency. The reason is this energy that you are pumping as a photon, get Q Hc by Q, Hc by lambda, Hc by this energy can never be actually greater than the voltage you are applying, equivalent voltage, because the sum of the voltage will anyways get wasted somewhere, right. So, anyways, what I try to say is that the law of conservation of energy says that the energy that you are supplying QV will always be greater than equal to the energy of the light you are emitting. That is why your wall plug efficiency will be always slightly lower than the external quantum efficiency. Okay. So, we will end the class here today. We have covered a lot portion of the LED. We have discussed about radiative, non-radiative recombinations and the rates. I told you about the bimolecular rate constant. We introduced the different efficiency terms, the quantum wells, double heterojunction LEDs. So, these are important concepts in LED literature that we should be familiar with. We have one more class of LED remaining. What we will do is that we will go through some of the loss mechanism like escape cone and total internal reflection losses, little bit on the maybe the brightness and the chromaticity and how human eye perceives the bright colored LED. Okay, all those things we will touch base in the next class. So, that we will conclude the optoelectronics section of this course. Okay, thank you for your time.